guys, welcome back to In Case of Econ Struggles. Welcome to another causal inference struggle. We've talked about instrumental variable regressions and estimation a lot on this channel. Today we're talking about it again, but specifically we're going to talk about why the first stage in an IV estimate is so important. The first stage again being your effect of z on x. So timestamps are below if you would like to jump around, but let's get right into the reasons why a first stage is so important. So the three reasons why having a large first stage or a large impact of z on x of your instrument on treatment is so important is because you're going to get more precise estimates for your IV estimate of the effect of x on y. And then if you have some minor issues with your instrument, a larger first stage is going to make those issues much smaller than they would be if you have a small first stage. Specifically, if you have a weak instrument or you have sample selection, the larger your first stage in your IV is, the less the impact of these two issues are going to be. And we'll see some examples later on that exactly demonstrate with some numbers how this is the case. But for now, these are just the three overall reasons why having a large first stage is good for your IV estimate. Just to remind you how we calculate an IV estimate, our goal is to calculate this purple arrow here, this estimate of x on y. How do we do that? Well, we take the reduced form, which is the impact of z on y, and we divide that by the impact of z on x, or the first stage. And remember that this first stage is also called our compliance rate, and this reduced form is called our ITT, or intent to treat. In this first stage, this compliance rate has to be between 0 and 1, where if it's exactly equal to 0, then it's not an instrument at all, and if it's a 1, then it's a perfect instrument. Let's talk a little more about why having such a large first stage gives you a more precise estimate of your IV estimate or your beta hat IV. Well, if you have a larger first stage, that means you're going to have even more variation in x that's specifically due to z and not some other factor. If you have that, that means you're going to get lower standard errors in your IV estimate, and we like lower standard errors because if we have lower standard errors, we have a lower confidence interval for our beta IV, and we can learn more about the world with our IV estimate than if we have higher standard errors. And just as a quick aside, if you have a perfect random control trial, then that's an instrument where you are assigned to treatment or not, and if it goes perfectly, if you have perfect compliance, then your first stage is exactly 1 with a very, very, very low standard error, which is why an RCT is sort of like a perfect instrument. Basically, what I'm saying is, if you have a really high compliance rate, if you have a really strong or really big first stage, then you're going to get a stronger relationship between z and y through x, and so your IV estimate is just going to be more precise, and you'll feel more confident about your IV estimate overall. So here's an example as to why having a large first stage is good for your IV estimate. So let's say we're in two worlds. In both worlds, the true effect of having a cat on your stress level is -2, where stress level is measured from 0 to 10, and having a cat is just a 0 if you don't have a cat, and a 1 if you do have a cat. In world 1, in the green world, let's say that you pick your name out of a hat, and that tells you whether or not you can adopt a cat. In this world, it's really strict. There's no one who can avoid the lottery, and there's no one who can sort of cheat the lottery. If you enter the lottery and you win, you absolutely get a cat, and if you don't win the lottery, you do not get a cat. The compliance rate is exactly 1. In the red world, you have to take a cat IQ test, but the cat IQ test is really sort of a formality. Lots of people who don't pass the cat lottery get a cat, and lots of people who pass the cat lottery do not get a cat. So maybe the first stage is like 0.10. Maybe the compliance rate is 0.10. So what's going to happen when I estimate the effect of z on y? It's the effect of z on y through x. So I'm going to get a reduced form in the green world of -2 with a standard error of like 0.1. Now in the red world, because I'm going through x, it's the effect of z on y through x. I'm going to get a much smaller reduced form. I'm going to get maybe -0.2 because again, my first stage was only 0.1, and when I follow the arrows in the arrow diagram, it's going to give me that my effect of z on y is 0.2. My standard error in the first stage, or in the compliance rate, is going to be really, really small in the green world because I have a perfect instrument. So I'm going to say it's like sort of close to 0. And in the red world, because I have a small first stage, my standard error is going to be sort of large, so maybe it's 0.4. Now, if I were to just use these standard errors in order to calculate my confidence interval, what I'm going to get is in the green world, my estimate, my 95% confidence interval for the estimate of the effect of having a cat on your stress level is going to go from -2.2 to -1.8, which is actually really pretty close to the true effect of -2. And again, we had a large first stage. In the red world, I have a very small first stage, and so I'm going to get a larger standard error. If I have a larger standard error, my 95% confidence interval for my IV estimate is going to be much wider. It's going to be so much wider that it's actually going to go from -9 to -1.2 if I did the math correctly. And as you can see, this is a huge interval. -2 is definitely in this interval, and I can say that having a cat definitely reduces your stress level at the 5% level. But what I can't say is that for sure it's -2 because this interval is huge. Why is this interval huge? This interval is huge because I had a higher standard error. Why did I have a higher standard error? Because I had a smaller first stage. So this tells you two things. First, it tells you why having a larger first stage gives you a better estimate or a more precise estimate of your IV estimate. Notice that the true effect is contained in both intervals, but I would much rather have a smaller confidence interval than a wider confidence interval. So this example tells you two things. The main thing it tells you is that if you have a bigger first stage, you get a lower standard error. And if you have a lower standard error, you have a tighter confidence interval. If you have a tighter confidence interval, you're going to be more confident in your IV estimate. If you have a smaller first stage, that is not going to be the case. And in particular, you're going to have a weaker instrument. Why do you have a weaker instrument? Because my instrument, my CAT IQ test, does not really affect my treatment or whether or not I get a CAT. That leads me to higher standard errors, and that leads me to larger confidence intervals in my IV. I'm less likely to be able to learn something about whether or not having a CAT reduces your stress level. I can say that it reduces your stress level. By how much does it reduce your stress level? I'm not really confident because -9 to -1.2 is sort of a huge interval. Just to make that second point a little more clear, I had a weak instrument in the red world because my first stage was 0.10. My Z didn't really affect Y through X. It's sort of weak in that term. So if I would have had a strong first stage, if that CAT IQ test would have led to a large first stage or a large compliance rate, then it probably wouldn't have been as big of a deal if the effect was lower because my IV estimate would have been more precise. My IV estimate would have been more precise. I would have been sort of more confident in interpreting that point estimate. Now let's talk about the other problem that IVs typically have, which is sample selection, or you could have a validity issue with your instrument. So here we've got two worlds again. We've got our green big first stage world and our red small first stage world. And let's say that in both worlds, what we have is that Z causes Y through X, but Z also causes Y directly through this other channel of -1. So again, maybe we have a slight validity issue. Notice that most of the relationship between X and Y is through Z, but there is a tiny part of that relationship that is coming directly between X and Y. So the true effect of Z on Y is just -3 minus 1 is -4. But if I have a small first stage, then this relationship here is just multiplicative. So this is 0.1 times -0.3, which is -1.3 in the end. The effect of Z on Y in our big first stage or our perfect first stage is 1, and our small first stage is 0.1. So if I were to just calculate the IV estimate, it's going to tell me in the big first stage that it's -4, and in the small first stage that it's -13. So notice that even though we had validity issues, when we had a large first stage, we still got pretty darn close to the actual true estimate. We actually got pretty close to the true value, which we said was -3. But if we had a very small first stage, we are very far from the true relationship between X and Y. So why did this happen? Well, notice that in the small first stage world, when we estimated the impact of Z on Y, because our first stage was only 0.1, when we tried to estimate the effect of Z on Y through this black channel here, we got -0.3 instead of 3. And so when we put in this slight validity issue, which was -1, we got a very different estimate in the small first stage world than we did in the big first stage world. So when we did this division by the first stage or the effect of Z on X, we got -13 in the small first stage world and -4 in the big first stage world. So this just goes to show you if I have slight validity issues, the larger my first stage is, the less that is going to impact my IV estimate, and hopefully this example sort of makes that clear. Just to wrap up, let's talk about the best to sort of least best options in terms of how my first stage is going to go. So ideally, I've got a big first stage, and I've got small standard errors in my first stage, and I've got small standard errors in my effective Z on Y as well. If I had to choose, I would like a big first stage and larger standard errors over a smaller first stage and small standard errors. For all the reasons we talked about, the big first stage is going to help me be more confident in my IV estimate than if I have a small first stage. And of course, last is both a smaller first stage and larger standard errors. But hopefully the examples we talk about sort of make this intuitive. If you still have questions, make sure to comment below. Otherwise, we will see you next time for another case of econ struggles.